Right. Answers. Live wire is brown and it's held at a potential difference of 230 volts. Now, your notes will have that information in there as well. And the earth wire is green and yellow, and it's always at 0 volts. Otherwise, you'll get a bit of a shock whenever you touch the appliance. State the frequency. The frequency is 50 hertz for UK main supply, and the average voltage that comes out of the plug socket is 230 volts. Now here you've got a fault where the live wire is directly touching the neutral wire. Normally what happens is current comes out of the plug socket through the live wire, through the appliance, then through the neutral wire and back to the power station to complete the circuit. Now here it's saying that the live wire is directly connected to the neutral wire, missing the appliance out altogether. So someone's messed up the wiring. So the neutral wire, what's the purpose of it? It completes the circuit. Now the current has to pass through the appliance before it gets to the neutral wire. But this has been bypassed because of the fault. So it doesn't get to the appliance in the first place. So the appliance has resistance where the energy is dissipated, but because it's bypassed it, so the overall resistance is quite low. And essentially, you've got short circuit. You can get a loud bang happening, but this question doesn't go down that route. It doesn't allow the current to go through the appliance, so it does not work. Two purposes of the insulation that covers the live wire. Remember, the color of the live wire is brown, and the color helps us identify the live wire. And the second thing is, if the live wire wasn't covered in insulation, we would get an electric shock. So the insulation prevents an electric shock. The next question. So the man switches on the iron and expose the live wire. He receives an electric shock. With reference to the electric potential of the man, explain why he receives an electric shock. Now, electric shock is a current flowing from one place to another. For a current to flow from one place to another, there must be a potential difference between the 2 points. So the man is at a potential difference of 0 volts. The appliance is at a potential difference of 230 volts. The current, so the live wire is held at 230 volts on average. And because now there's a potential difference between the man and the appliance or the live wire, a current will flow from the live wire through the person, giving them an electric shock. Okay, so there must be a difference in voltage between 2 points for that electric shock. So the difference in voltage here is 230 minus 0, so there's a 230 volts difference. So wherever there's a difference in voltage or potential difference, a current will flow through those 2 points. A socket is switched off and an iron is unplugged. Explain whether there is still danger of the man receiving electric shock from the plug socket. Well, it depends how close you are to the plug socket. If your fingers are hovering over the pin where the live wire goes in, then there is some danger. The socket is still at a potential of 230 volts. Okay, and the electricity can still flow through the person with a potential difference of 0 volts. So that spark can jump through the air and into you, and then you can get an electric shock. The closer and closer your finger gets to the live wire, the potential difference will be big enough between the two where the electricity can jump through air, and if you get even closer, you will get more chance of an electric shock. This first sentence is pretty straightforward. The power of an electrical appliance is the energy transferred per second. That's the definition for power. Energy is transferred because current does work against the appliance resistance. So every part of the circuit where there's a component has resistance. And because the current does work or transfers energy at the place of resistance, it would change into different forms. The equation, you can write it like this: energy is equal to power times time, or power is energy divided by time. Calculation, no need to convert units because watts and seconds, those are the standard units, and then 50 times by 20, that's 1000, and 1000 joules. Now what the child has done is they've put the speed to 75 watts from 50 watts. So the higher the power, the higher the rate of energy transferred from the battery per second. What type of energy? Chemical energy transferred from the battery per second. So it's going to run out much more quickly. You've got a washing machine, two different modes. A standard mode, the power is 600 watts. The washing machine will run for 125 minutes. Then the economy mode, the power's at 400 watts, and the time it will run for is 160 minutes. So the energy transfer, the useful energy transfers of electrical energy from the mains to thermal energy in the water in the washing machine, and kinetic energy of the drum that spins and washes the clothes. Those are the two useful forms. The formula is work done is energy equals, sorry, the work done is energy transferred. Just remember, when they ask you to calculate work, they mean calculate the energy. In the picture above, you've got power and time. So you know that the formula that we need is energy equals power multiplied by time. So we've got the power. So when in economy mode, the power is 400 watts. The time is in minutes. Okay, so we need seconds. So what we've got is 160 minutes in economy mode. So that's times by 60 seconds, and we'll get the total number of seconds, and we get a total energy of 3,840,000 joules. Now, this is a more difficult question. Calculate the energy saved per cycle using economy mode instead of standard mode. So we've just worked out how much energy we need in economy mode. We'll work out how much energy is needed in standard mode, which is 600 watts times by 125 minutes times by 60 seconds. That'll give the time in seconds. That's how much energy is used in standard mode, 4.5 million joules. And it says how much energy is saved per cycle. So that means that the energy from the standard mode minus the energy from the economy mode, giving us an energy of 660,000 joules. And the last page, a power source supplies energy to a charge. When a charge passes through a component with resistance, it does work so that the charge's energy decreases. So when current flows through a circuit, it takes energy from the battery or from the power supply, and it delivers it to different places. So where the energy is delivered, there is work done, and the charge will lose that energy and deliver it to the place, let's say like a lamp, and that energy, electrical energy, will change into light energy and thermal energy as well. Now, the equation that links potential difference, charge, and energy, you can write it like this: potential energy, the potential difference is equal to energy divided by charge, or you could have written energy is equal to potential difference times by charge. Now, the charge is 2 coulombs. The potential difference, they've told us the voltmeter reads, there's a voltmeter 6 volts. We want the energy transferred in lamp X, so there's your potential difference of 6 volts. Remember, potential difference and voltage are the same thing. So 6 times 2, that's 12, and energy is measured in joules, so 12 joules of energy. Now it says that when you multiply the potential difference with the current through lamp X, so what's the potential difference through lamp X? It's 6 volts. What's the current through lamp X? Well, it's the same reading as the ammeter, and the ammeter is reading 2 amps. So when we multiply these two up, potential difference and current, so 2 times by 6, we get the same number of 12. But potential difference times by current is actually the power. So what you've effectively worked out is 12 watts of energy, or 12 joules per second is delivered. Okay, whereas this was just the amount of energy that was delivered. So considering that current is the rate of flow of charge, that's where the second comes in, and that changes it into the power. Question 2, power is current times potential difference. As the other formula, rearranging it is current equals power divided by potential difference. That's 75 watts divided by 230 volts, and that's 0.33 amps. I've rounded that. The next one is the other formula that links power, current, and resistance. Power equals current squared times by resistance, and we want to work out the resistance. Given that we've got the power and the current, and resistance is equal to power divided by current squared, by rearranging that, and that gives us 2.5 divided by 0.5 squared, and that is 10 ohms. These formula are all in your notes. So when you have been going over these, I hope you have referred to your notes or the textbook.